Hi all, we are now at the last part of one-dimensional motion, and we're going to be talking about free fall today and what is free fall. And then we're also going to do some application problems where we actually do some where we quantify and actually solve for problems just like in our homework. Okay, so if you haven't done any of the reading, please go ahead and do so now. Okay. And again, chapters 1, 2, and 3 in Coletta. In OpenStax, if you're in college physics, chapters 2 and 3. And in physics 121, please do 2, 3, and 4. All right, let's go ahead and start. So we're going to have to talk a lot about, when we begin to talk in a few minutes about what free fall is, we're going to have to begin by talking about what is y direction motion. So y direction motion is up and down motion. So just like x direction motion, you're going to have a 0 meter mark in the y direction motion. And you're going to also have, so anything with a position that is greater than 0 is going to be above the origin. Anything with a position lower than 0 is going to be below the origin, okay? And so what that means is for velocity vectors that are moving in the positive y direction, that they're going to have an upward motion, and velocity vectors that are moving downwards are going to have a negative y direction motion. So up is positive y, down is negative y, and that goes along with the acceleration vectors. If the acceleration vector is pointed up, then it's going to have a positive acceleration vector. If the acceleration vector is pointed down, then it'll have a negative acceleration vector. Okay? So what is free fall? So in our lives, we experience only the type of motion with a resistive force due to our atmosphere. So when you when you drop a ball or drop a piece of paper or anything like that, air resistance begins to stack up. Okay? And it quickly takes something that is speeding up and turns it into a constant velocity, right? And the best way to think about y direction, falling objects is that they're really sinking, really. In air is much like water. It's just, it's a compressible fluid. So air is a compressible fluid. Water is not. And so if you've ever dropped a rock in the water, you'll notice the rock will actually kind of speed up for a little bit, and then it'll do this kind of thing where it starts to wave back and forth, just almost like it's dodging left and right. Well, when you kind of think about it, leaves falling from a tree do the same type of motion. They'll speed up, and then when they hit their constant velocity, they're now falling at a constant speed. And they kind of do this back and forth type of motion. So we never really get a chance to experience free fall. Okay, and free fall is motion without an atmosphere. Okay, and that is very hard to imagine. Okay, and the best way to do that is to actually, there's an experiment, there's a great little problem that I could show you, and I'll attach a link, and that is when the Apollo moon landings, okay, where they drop a feather, a falcon feather, and a hammer on the moon. The falcon feather and the hammer on the Earth the hammer would hit the ground before the feather does, right? But on the moon, without air resistance, the falcon feather and the hammer hit the ground at the same time. So here we have the video.
Solar wind and penetrometer drum in the ETB.
So here we have the lunar mission.
Yes, I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer.
So right here, in his right hand is a hammer, and his left hand is a feather. And he's about to drop them in a few seconds.
I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
So this is a good example of free fall, because on the moon there is no atmosphere, and it has a gravitational environment, and it's only 1/6 of the Earth. But if you notice, the hammer, which is in his right hand, and the feather will fall at the same rate, and notice they're both right next to each other. And then right before they hit the ground, they're right next to each other, and now they have hit the ground at the same time. So on the Earth, in a similar situation, if we remove the atmosphere of the Earth, all objects would drop at the same rate, and they would all have the same acceleration of 9.8 meters per second squared. Okay? So when we talk about free fall, we're talking about falling objects in a vacuum or without an atmosphere. Okay? And they are purely only under the force of the Earth, and they're also falling at 9.8 meters per second squared. They're accelerating. They have an acceleration downwards at 9.8 meters per second squared. Well, again, you could really see this effect by just dropping a ball and then dropping a piece of paper. And then when you crumple up that piece of paper and that ball are almost dropping at the same rate, right? So basically, in a non-free fall situation with an atmosphere, you have objects sinking, and so it's the density of the object that determines the rate of acceleration, okay? But if you remove the atmosphere, this piece of paper and this ball would hit the ground at the same time, just like the falcon feather and the hammer. And so here's a table which is really interesting, because even though we basically have said the Earth's acceleration, gravitational acceleration, is 9.8 meters per second squared, it really, depending on the size of the Earth at that location, the Earth bulges as it spins. So it's kind of more of an oval versus a perfect sphere, but it bulges a little bit on the equator. And what you find out, since you're on the equator, closer to the equator, the Earth, that bulge on the equator, you are not actually at 9.8. You're actually at 9.78 meters per second squared. And the closer you get to the North Pole, now you're closer to the center of the Earth. And so that gravitational, that level of gravitation is actually going to be a little bit greater than 9.8. So what we kind of do is, overall, we're saying on average, your gravitational acceleration vector downwards is going to be 9.8 meters per second. And that's pretty much, it's almost like an industry standard when we talk about physics and physics textbooks, okay? So free fall is a situation where all objects are falling with an acceleration vector of 9.8 meters per second squared down. Okay, and they do not have an atmosphere, so there is no air resistance. Okay, and here's that same table up close. Well, let's talk about this. Well, now if we're talking about an object, you're just holding a ball up in the air at a height of 78.5 meters off the ground, all right, or off a cliff, okay, and the cliff is 7.85 meters down below you, okay, and then you let the ball go. So its initial velocity is 0. Well, now, after the first second, now it's going to be at a velocity of 9.81 meters per second, and so that's what that vector is, and I'm going to mark up this document by hitting the comments, and so now I have tools. So now you could say this vector is 9.81 meters per second. Okay. And then you're going to be adding another, that acceleration vector is going to add another 9.81 meters per second to this. And now this next vector is going to be 19.6 meters per second, which is 9.8 plus 9.8. And then, so now we're traveling at 19.6 meters per second. And then you're going to add another 9.81 meters per second squared to that, or 9.8 meters per second for the next second. And now it's going to be falling at 29.4 meters per second, or 9.8 plus 9.8 plus 9.8. And now finally, after the fourth second, you're going to be adding that same acceleration vector to 29.4, and you're going to end up with, right before it hits the ground, 39.2 meters per second. And it's going to hit the ground at a depth of 78.5 meters below, and these should be Y, not X. So they should be below the initial position at the top of the cliff, or this is where you're standing and you're watching it fall below you. So these are negatives below you, okay? Well, now, if you graph the velocity in the y direction versus time, you can see at time 1 it was negative 9.8. It started off at not moving at 0 seconds, and then after the first second it was 9.8 meters per second, and then it accelerated for 9.8, and then becomes, that adds to it, the original 9.8 and becomes 19.6, and then you're going to add the acceleration vector again to 19.6, which is going to give you 29.4 at the third second, okay? And so this line is going to make a constant, acceleration line, and it's going to be at negative 9.8 meters per second, okay? The cool part of this is really interesting. Had this been shot up, it would be at an initial speed of 39.2 meters per second. It would be accelerating down at negative 9.8 meters per second squared. And then at this point, it would be traveling at 29.4 meters per second. And it would be at this point right here. So let's say you're standing down below here at 78.5 meters, and you shot the ball up with an initial velocity at 39.2 meters per second. Well, it's right here. The next point, it would actually be right here and be traveling at the same speed, just directed upwards. And at this point, it'd be traveling at the same speed here, 19.6 meters per second, but directed upwards. These are downwards. And then at this point, it'd be traveling upwards at 9.8 meters per second. And then at this point, it would come to a stop. So it would do the exact same motion if you'd launched it upwards at the same speed, and it would be at the same point, but just the velocity vectors would now be directed upwards, but it would be the same magnitude. Okay, and that graph would actually look something like this. It was directed upwards and it would slow to a stop. And then when it got to the top, it would then continue on and actually be doing the same thing this way. So it would be going up at positive 39.2 meters per second, your launching speed. And by the time it came back down, it would be traveling down at 39.2 meters per second. Okay? And at the halfway point, which occurs right here, okay, it would be 0. So this again is like where it has a positive velocity upwards, and then it turns around at the top and then goes down. And if you'll notice, it's accelerating down at negative 9.8 meters per second squared the entire time. So this is a cool situation when things are in free fall. They're their motion upwards is their same motion downwards. Okay, it's just the velocity vectors are reversed. Okay, this is the reason why you don't fire a gun in the air, right? Because if you shoot a bullet upwards in the air, it'll be going upwards at the muzzle velocity, come to a stop, and then it'll be coming down at pretty close to the same muzzle velocity, if not the same muzzle velocity, right? So that's why guns are dangerous and why you don't shoot them up in the air, okay? Well, now that we're dealing with motion up and down, now our velocity, our motion equations are going to incorporate gravity, and we're going to always direct that gravitational acceleration downwards. So we're going to just make sure that we call downwards as negative in the negative y direction and upwards in the positive y direction. Okay? And so the velocity versus time fit is going to always have a downwards directed acceleration. And that means that on a y versus t graph, that acceleration component is going to be directed downwards, regardless of the initial velocity vector being up or down. And when we merge those two equations, these two equations together, and we get the other two equations of motion, this one right here at the bottom, it's going to have a downward directed gravitational acceleration too. Okay, so we have to kind of alter our equations for gravity, and gravity we're going to just say it is pointed down at 9.8 meters per second squared. Okay. And so when we graph a y direction motion, okay, so let's suppose we shoot a ball up at 7.3 meters per second, okay, and it leaves your hand and you're holding it and you're 1.5 meters tall, okay. So when you shoot it here, you're throwing it with an initial velocity of a positive 7.3 meters per second. Well, when this ball is coming back down into your hand, it's going to be traveling down at 7.3 meters per second, based on what we just learned right here. If you shoot a ball up at 39.2 meters per second, it's going to be in these same places as it is when it is coming back down, and it'll be coming back down at 39.2 meters per second. And that is because gravity is always constant and is always down at 9.8 meters per second. Okay? And so at the halfway point, at the half time of flight, this is also really interesting because the velocity is 0 here. And this is the point in the y versus t graph where the motion, where the velocity in the y direction comes to a stop. This is where it goes from moving up and then slowing down as it's moving upwards, and it slows to a stop. And now it's turned around, and now the ball is going to be traveling straight back down and speeding up as it's moving down. And that's in the negative direction. So it's going to, from positive 7.3 meters per second upwards, it's going to slow to a stop, and then it's going to speed back up to 7.3 meters per second as it's coming back down. And that's what these equations are saying. Okay? So this is free fall motion, or motion up and down. Okay? So we're going to be using this when we move on to our application problems. And I think we have one application problem that is a rocket problem. We're going to really need to think about how we use this. But essentially, we're going to be using the same approach when we do everything. So again, with free fall motion, when in a y versus t graph, when you shoot a ball up on a y versus t graph, it's going to start off with an initial positive velocity, and that positive velocity, since it has a negative acceleration associated with it at negative 9.8 meters per second, or an acceleration vector down at 9.8 meters per second, is going to eventually slow to a stop, and then it's going to speed back up to its original speed. that you shot it out at, okay? And that what that's saying is here, it starts off with initial positive velocity, slows to a stop on a velocity versus time graph, and then speeds back up to its initial velocity but directed downwards. So it's initial speed but directed downwards, okay? So it's a cool kind of thing that we could, it's very uniform in the way its approach is, okay? And at the very halfway point in the total time of flight, the velocity will always be 0. And it will also be at its highest point. So it'll be at its maximum height. Okay, and that is determined by the initial velocity you give it upwards. Okay. And so that occurs at the half time of flight. So this is if this is 0 seconds, this will be 1 second, and this will be 2 seconds, right? So this maximum height will occur at the half time of flight, and that'll also be where the y direction velocity is 0. Okay, as seen right here. So it's very uniform, and that, again, that's because the acceleration vector is constant down. It's even accelerating at this moment right here. Even though its velocity is 0, it still has an instantaneous slope right here, or an instantaneous acceleration of a negative slope of 9.8 meters per second squared. Okay? So for everything that we've done, we're now going to apply a tactics. What we're going to do is we're going to try drawing a motion diagram to illustrate what we're looking at. And when we're doing that, we're going to try to draw a motion diagram and give our displacement vectors and our acceleration vectors. And that means we're going to have to establish a coordinate system. It might help to sketch the situation. And then what we're going to do is define our everything that we know. So we're going to define our knowns and our unknowns, and we're going to list those out. And then what I would like to do is I also like to list our equations of motion too, and see what we have, what variables we have to work with, and that way we could kind of figure out what to use. And by doing all this, what we'll do is we'll keep in mind the direction of our velocity vectors and acceleration as being positive or negative or even 0 at any point. Okay, so we're going to keep this set of tactics, which is very brief, and what we've been learning and striving up to actually do these quantitative problems. So let's get into it. Okay, so here we go. We are driving to the grocery store at 20 meters per second, and we are 110 meters away from an intersection when the traffic light turns red, and you start to begin braking instantly. We're going to assume that our car brakes are working at a constant acceleration, so our car isn't skidding. How long does it take for us to stop after the light turns red? Okay, so let's start with our first situation here. So we're going to try to draw a motion diagram. Okay, so we're going to draw a motion diagram, and I'm going to say that we are going to be driving horizontally in the positive x direction. Okay, and we just crossed the 0 meter mark. Okay, when we realized that the light, and here's where the light is, the intersection is. Okay, here's where the intersection is, over here on the right hand side, is just turned red. So that means we start off moving really fast in the beginning and then start to slow down over time. And let me see so when we start to hit our brakes is at the 0 meter mark, we start to cross, and now our positions are positive. So here at the 0 second mark, we're right here, and then here's 1 second mark, 2 second mark, 3 second mark, 4 second mark. And I'm just putting times there. I don't know if those times are actually real. And let's just say at this point, I'm going to move our intersection to be right here and at the 5-second mark. And this is at 110 meters away. Okay? So pictorially, I'm thinking that it's doing something like this. We have a large initial positive, since we're started here at the 0-second mark, we're going to be, our initial velocity vector is going to be that, our initial displacement vector is going to be that big, and then it's going to be a little bit smaller, and then a little bit smaller, a little bit smaller, a little bit smaller, and finally it's stopped. Okay? And start. So that's what I'm guessing what our vectors are doing. Okay? And so what this is telling me is that our displacement vectors are going to be positive, or rather our velocity vectors are going to be positive, but since they're getting smaller over time, we're going to have negative acceleration vectors associated with those at each and every point. And they're going to be the same size acceleration vectors at each one of these points. Okay? So here, I feel like I've got a really good, I feel like I've done a pretty good job at sketching the situation and our coordinate system. Positive x is to the right, negative x is to the left. We're just crossing the 0 mark and trying to stop here at a position of 110 meters, which is where the light is at. Okay? All right, well, let's list off what variables that we have. Okay? Well, we know the initial velocity is 20 meters per second. So we know this is positive 20 meters per second, in that we're traveling at a positive 20 meters in that first second. And we know we're going to want to come to a stop at 0 meters per second. So we want our final velocity, so this is our initial velocity, we want our final velocity to be 0 meters per second. Okay, and we also know that our total displacement vector from beginning to finish is going to be 110 meters. So it started here at 0 meters, and we're going to get to a positive 110 meter position from 20 meters traveling at positive 20 meters in 1 second to 0 meters in 1 second. Okay. So the question is how long does it take for us to stop once we realize the light is turning red? So we're going to be trying to find what is delta t. What I also like to do, which they don't list off here, is to list off any variables that I don't know. And we don't know acceleration. So we don't know acceleration. So what I'm going to do now is I'm going to list off all of our equations of motion. Okay? And the equations of motion are x final minus x is equal to x initial. So final position, initial position, plus vit, and our acceleration is going to be negative 1/2 at squared. And I'm putting in that we have a negative x direction. We have an acceleration vector pointed to the left because we're slowing down. We're moving to the right and we're slowing down. That means our acceleration vector has to be to the left. We also have this. We have the velocity versus time fit, which is going to be a positive initial velocity minus an acceleration versus time. Okay. I think we had, what is it, v final squared equals v initial squared plus or minus 2a, and this is going to be delta x, which is going to be x final minus x initial. And then finally, we have x final equals x initial plus vi plus vf over 2, and this is delta t. Okay. Well, the reason why I listed out the a variable and crossed it out is I want to use the quickest equation to get at what I'm trying to find. Okay, so we don't have the acceleration. Okay. So we don't have the acceleration vector, but we do have initial velocity vector. We do know the final velocity, and we know the displacement, and we're trying to find time. We don't have acceleration. So for now, I'm going to isolate any of these equations which has acceleration on it, and I'm going to put a red X through that because we don't have those acceleration vectors. That tells me we don't want to use this top equation. We don't want to use a second equation. We don't want to use a third equation. In order to get delta t, we're going to use this bottom equation. Okay? And that is because we don't have the acceleration. And we could find it if we wanted to, but I would rather just do the problem. So delta x here is going to be, x final is going to be 110. And we have x initial, so we're going to be using this equation, and it's going to be plus the initial velocity vector plus the final velocity vector over 2 times delta t. And I'm going to solve this for delta t. In order to do that, I'm going to bring the x initial onto the other side. So x final minus x initial equals v final plus v initial. Sorry, I reversed those two. I will keep those in the same order. So v initial plus v final over 2 delta t. I'm going to multiply both sides by 2 and divide both sides by vi plus vf. And that gives me x final minus x initial. And this is going to be 2 divided by v final minus v initial, which is equal to delta t. And now I'm going to plug in our variables. Well, x final is 110 meters, x initial is 0 meters, v final is 0 meters, and v initial is 20. So basically, x final minus x initial is 110 meters, and this is 2 divided by v final is 0, v initial is 20 meters per second, and that's delta t, and this is going to work out to be 2 divided by 20, which is going to be 1 divided by 10, and so now we have 110 meters divided by 10 meters per second, which is going to work out to 11 seconds. And that is the amount of time it takes for me to come to a stop. So when I was estimating my times, I was just kind of putting some numbers in place. So this final time should actually be at 11 seconds. And that's the amount of time it takes for me to come to a stop. Okay? All right. Well, let's do another problem. I hope you learned from that. And we're going to do that same format. Okay? Except this time I think I'm going to use whiteboard because I was getting a little nervous. I was running out of space. All right, so on this problem, I'm going to actually copy it over to whiteboard. And the great thing about whiteboard is you could use it. So you could use this and then include other people in on your whiteboard. So I'm going to copy this next problem in our notes over to whiteboard. And if I wanted to invite other people to this, I would just hit this plus button right here and hit a sharing link. and create a link and then copy other people over to it. But for now, I'm just not going to do that. So let's go ahead and we're going to do the same thing that we just did. We have a person running a 100-meter dash, and we're assuming the sprinter is running with a constant acceleration until they reach their top speed, and then maintains that top speed or that constant velocity through the finish line. So they're going to be accelerating to the point where they hit a constant velocity, and then they maintain that constant velocity all the way until the finish line. So the sprinter can reach their top speed of 11.2 meters per second in 2.4 seconds. What's the total time of the 100-meter dash? So, all right, so let's draw again. We're going to now draw a motion diagram. Okay, so I'm going to draw a line. And to the left is negative x. To the right, I'm going to extend this, is the positive x direction. And I'm going to say that they're going to be starting off at the 0-meter mark. Okay? And then they're going to be ending the 100-meter dash over here at the 100-meter mark. Okay? And so they're going to start off here not moving at 0 seconds. And they're also going to have an initial velocity of 0. So their initial velocity is going to be 0, right? That wouldn't be a fair race if you were already moving and somebody else was not was already running in front of you, right? So here we go. So this person is going to be starting out not moving, and then they're going to start a little bit. They're going to be speeding up, so their displacement at 0 seconds, and we'll call this 1 second. This is going to be 2 seconds. And then it's going to get a little bit bigger. You know what? Maybe what I'm going to do is I'm going to do it in terms of blocks. So I'm going to say they're here in the first block. And the second block is they're here. And the third block, they're here. Actually, we'll do this in half seconds. So, half seconds, 1 second, 1.5 seconds, and then we'll put 4 blocks here, which will be 2 seconds, which is about 2.14 seconds. And from now on, they're maintaining 4 blocks every time. And just to make it even more interesting, and this is all just subjective, I don't even know if this is happening. Here's going to be the 110-meter mark. So this is going to be 2.5 seconds, 3 seconds, and then let's say this, at 3.5 seconds, that's when they finish the race. And the reason why I was doing this so I could actually see the motion really well. So the velocity vectors, I'm going to use red. And now they hit their constant velocity at 2.5 seconds, and that should be a 5 there. And now they hit their constant velocity at 2 seconds, and then they maintain that throughout the end of the race. And that means our acceleration vector is going to be a 1-block acceleration vector that we're adding to each one of these. These first few seconds, and then the acceleration is equal to 0. The acceleration is equal to 0. The acceleration is equal to 0. And that's because they hit their top speed at 2.14 seconds. So, and also let's put it this way too, that at this point right here, at their velocity is 11.2 meters per second, and that is their speed at which they accelerated to. Okay. We'll call this the velocity 2. The initial velocity is going to be 0 meters per second, and I'm thinking that we're actually just going to call this v final for the accelerated portion part, right? So that occurs right here at 2.14 seconds. So they've hit their top speed of 11.2 meters per second at 2.4 seconds. All right. Well, let's list out what we have. We have an initial velocity at 2 meters per second, an initial position of 0 meters. We don't know the position where they hit their top speed at when they're accelerating. We don't know what that is. My guess is we have to figure that out, because after that it just becomes a pretty simple constant velocity problem. Okay, so we don't know, and I think this is one of the things that we have to find, is their speed at which they hit their top speed, and that is occurring at this point of 11.2 meters per second. So I think this is what we need to find first. So we're going to solve the first part of the motion here, and we're going to find out what position they actually hit that top speed of 11.2 meters per second at 2.14 seconds. Okay, and then after that we're going to apply a constant velocity of 11.2 meters per second, from there on out. And this should occur from 0 seconds to 2 seconds. So pretty cool problem. So let's go ahead and I'm going to zoom out a second, and I'm going to list our equations of motion right above here. Okay, so we have a reference sheet, and the first is x final equals x initial. So I always do my position versus time curve fit, and since the object is speeding up, it's got a positive velocity vectors and positive acceleration vectors. This acceleration component is going to be positive, and that relates to this. It's got a positive acceleration here. Let's do x final equals x initial plus vi plus xvf over 2, and this is times t, and then v final squared equals v initial squared plus 2a delta x, and delta x again is x finals minus x initial. Alright, well, we don't have in this entire problem, we have initial velocity, we have final velocity, we have initial velocity, we have initial position, we're trying to find the final position at this accelerated motion part. We do have the time, and we do have final velocity, but we don't have acceleration. So any of these equations that have an acceleration in it, we are not going to use, which means we're going to have to use this. Okay, so we're going to use this to find the where this occurs right here, which is x final minus x initial plus vi plus vf, and luckily those are both positive. Well, one of them is 0, and this is delta t. Okay, So x final is what we're trying to solve for, so we don't have to use any algebra. Our initial position is at 0 meters, plus our initial velocity is 0 meters per second. Our final velocity is to the right at 11.2 meters per second. And this is divided by 2. And delta t is going to be from 2.14 seconds, and you started out at 0 seconds. Okay, so let's go ahead and figure out what this is. So 11.2 divided by 2, I'm going to pull out my calculator. 11.2 divided by 2, so 11.2 meters per second divided by 2 seconds. 11.2 meters per second divided by 2, is 5.6. And 2.14 seconds minus 0 seconds, so we're just going to multiply this 5.6 by 2.14 seconds. And that's 11.98 meters. So this person reaches their top speed in 11.98 meters. Okay? And let's just make sure that makes sense. Okay? So this is about 30 feet, so this is a really far distance. 110 meters is very far. So let's double check our math. They started out not moving at time 0, and at 2.14 seconds they were at 11.2 meters per second over 2, and this is delta t, so that does make sense. So this is going to be 11.98 meters per second. Cool. So that is accelerated motion for here. Well, now at position here, I'm going to now fill this in. This occurs at 11.98 meters per second at time 2.14 seconds. Well, now they have to get from this position, 11.98, to 110 meters. Okay, and we need to know the time that they do it. It's got a constant velocity now. Okay, so we're going to try to find the time it takes to get to here, and we could actually use the same equation here, except we're going to be using it to solve for time. Okay, so here now I'm going to write for this portion, the second type of portion, which is a constant motion portion. We are now at a time, and this is the new initial time, which is at 2.14 seconds. And we are at the position of 11.98 meters per second. So I'm setting up almost like a new problem. 11.98 meters is our initial position at that time of 2.14 seconds. And I'm traveling at a constant velocity, which means our final velocity and our initial velocity are both going to be a positive 11.2 meters per second. Okay. And then our final position is going to be 110 meters, where we started here. And now we need to find the final time. Again, we don't have acceleration, so I think our best shot is to use the same equation. So x final, which is going to be 110, x initial, plus vi plus vf all over 2, and this is going to be t final minus t initial. So this is delta t right here, and I should put this as delta t. Alright, and we're going to be finding for that t final. Okay, well, the first thing we have to do is we're going to be solving for this portion, is we're going to subtract this x initial onto the other side, and now we have v initial plus v final over 2, and that's t final minus t initial. Okay, now we're going to multiply both sides by 2, divide both sides by this, So I'm going to actually put parentheses around this and keep it there. But I'm going to actually use this as a fraction. The 2 is going to come to a top. The VI plus VF is going to be on the bottom. So just kind of flip-flop that fraction. And then you have T final minus T initial over here. Now you just add the initial time of 2.14 seconds, or the time here at this point when we started our constant motion, over to the other side. X final minus X initial. And then we're going to, this whole thing, we're going to be just adding the initial time. And that is going to be our final time. That, okay. And so now, since we have it solved in terms of variables, let's go ahead and put on our numbers. So this is going to be 2, and V final and V initial are the same numbers. You're going to be adding to the same number here. They are the same numbers, and this does work. Okay. The initial position is this midpoint position where he stopped accelerating, and that happened at 11.9 meters. I don't know why I put meters per second here. Let's get rid of that part. So that happened at 11.98 meters. He's going to ultimately end the race at 110 meters. And then we're going to add our time at that initial position of 11.98 meters. Right there is 2.14 seconds. And that's going to be our final time. All right. Well, let's pull out the calculator. Okay. So, let's erase that. So we have 2 divided by parentheses. I'm going to do this part. 11.2 plus 11.2, and then I'm going to end parentheses and hit enter. And so this is 0 point over here. This is going to be 0.89, 0.089. Let me just double check that. So that's 22.4. Let's just double check. 2 divided by 22.4, and that is the same thing. So this is 0.898. 0.089 meters. Actually, it'd be seconds over meters. And this part here, is going to be 110 meters minus 11.98 meters, and that is 98.02 meters. 98.02 meters. And then we're going to add, so the multiplication, we're going to multiply this out, and we're going to add 2.14 seconds to that. And that'll be my ultimate final time. Okay? So 98.02 times 0.0, so I'm going to multiply that by 0.089 seconds over meters, which is going to be 8.72 seconds. 8.72 seconds. So this is going to be 8.72 seconds plus 2.14 seconds is going to be our T final. And let's see what we got. We're going to add to that plus 2.14. which will be 10.86. So it looks like this sprinter is going to take 10.86 seconds to finish the race. Okay? So this is an example of a problem where you have a speeding up situation and then going to a constant velocity situation. And we used all the steps. We put it into a motion diagram and then we divided it. We used all of our variables. Okay? All right. Well, let's try another one. Okay? And this will be our last problem. Okay? I want you to try this other problem when you get the chance. Okay, this last problem, the very, very last problem, I want you to try on your own. And we'll do this during our WebEx sometime in class. But let's do the Rocketmodel problem. And this is with a free fall situation. Okay, so you have a rocket that's going to be blasting off. Okay, and I'm going to go ahead and grab this. And I like using whiteboard for solving problems. So I'm going to move it over to here. And we're going to try it over here. Okay. So we have a rocket blasting off, and it's going to be moving upwards with an acceleration of 18 meters per second squared until it reaches a height of 30 meters. At which point its engines are going to shut off, and it's going to continue its flight in free fall. Okay, so this is a really cool problem because it does this thing where it starts off at the bottom at a position of, so at t initial, at time 0, it's at an initial, and I should say a y direction, not x direction. It's an initial y direction of 0 meters. Okay, and then they say basically this thing is going to be, this is 1, 2, 3, 4. It's going to be speeding up as it's moving upwards. Okay. And it's going to be accelerating from rest. Okay, and this is seconds. So all of this stuff is 0 at the beginning. And so it's going to be speeding up as it's moving upwards. And then something happens right here. And the engines shut off. Okay, so this is 0 seconds, 1 second, 2 seconds, and actually I'll put those times here. This is 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, so it's speeding up, and then it's going to immediately go into free fall, which means it's going to begin slowing down. So now, now it's going to begin slowing down. And it's going to eventually slow to a stop. This is 5 seconds, 6 seconds, 7 seconds. And I'm going to say V final equals 0. So it's going to speed up to this point right here. So it's going to have an acceleration vector upwards. The acceleration vector is going to be pointing upwards at each one of these points in time. And then at this point right now, then its acceleration vector is going to be in free fall, which now it's going to be acceleration vector is going to be at gravity pointing down at each one of these points. And the velocity vectors are pointing upwards, and it's moving upwards in the positive y direction the entire time. So up is going to be positive y, down is going to be negative y. So now we have our coordinate system and we have a good situation. So when it hits at some point, when it reaches a height of 30 meters, so now I'm going to say put in the meters, starts off at 0 meters here at time 0, and then when it hits a height of 30 meters, its engine shut off, and now it's accelerating down at 9.8 meters per second. So we, just like that last problem, we have to apply two different types of motion. One where it's speeding up as it's moving upwards, and one where it's slowing down as it's moving upwards. So it's speeding up as it's moving upwards because its velocity vectors and acceleration vectors are in the same direction. And then it's slowing down as it's moving upwards to come to its highest height at some final y. This is what we're ultimately solving for. Okay? Okay. And I'll just give this a 1. And this is the initial, ultimately initial position. Okay. Well, let's do the first part of the motion. Let's just do the speeding up portion. So the speeding up portion. And then this, from here to here, will be the slowing down. So this is the slowing down portion. And this is the speeding up portion. So let's do the speeding up portion right now. Well, let's list out the variables that we have. It starts off an initial position of 0 meters at time 0 with an initial velocity of 0 meters per second. Okay. We do know it's accelerating at 13, upwards at 13 meters per second squared. Okay. And then it's going to reach a final final height, and this is y1, where it's speeding up, and it basically runs out of fuel at that point at 30 meters. Okay. The engine shut off, and from here we're going to have to do a slowing down portion. Okay, so what we don't have is we don't have the final time that happens. We don't know what that is. Okay, and I think that's what we have to solve for to get that final time, because we have pretty much everything that we need. Okay. But I think we're ultimately going to, we're eventually going to solve for the height that it gets to be at. So we don't know what its final velocity is, and we don't know its time that it has. So maybe what we could do is, we'll play with it and see what we have. So we're going to try to find the final velocity. We're going to try to find the velocity at this point at which it is now going to be falling down. So we need to know what this velocity is right here. This blue velocity. Okay? So let's try it. Let's list off our equations. I'm going to try to see if I can go over and grab them here. And of course they're in the x direction. So what I'll do is I'll list them off over here. And I'll try to input the components that we're working with. So I always start off with the position versus time graph. In this case, the y final, y initial, plus VIT plus, in this case, the acceleration is due to the rocket, so it's going to be 1/2 AT squared, right? And we don't know the time that happens. All right, let's do the V final. V final is going to be equal to V initial plus AT. All right, and those be plus, well, those are both 0. Let's go ahead and let's do V final squared equals v initial squared plus 2a, and this is going to be delta y, which will be y final, y1 minus y initial, and then we're going to have y final equals y initial plus the initial velocity plus v1 all over 2, and this will be delta t. Alright, and these should be delta t's as well. Okay, well here's the variables that we have. We have y, we don't know v final, we don't know t final. My guess is that we need to find v1 first in this problem. We need to find the velocity right here. What is the velocity at this point right here? What is the velocity at this point? Because I think that once we have that, then we could actually figure out the height that it gets to. The other option is actually get is getting t final. Well, t the time that this we hit the 30 meter mark too. So we could actually go ahead and get both, because I'm not sure which one's going to be more useful. Okay. Because, and the reason why I'm saying this is that here we have two unknowns. We don't know v1. This is v1 and also delta t. Here we don't know what delta t is, but we do know everything else. And over here we have we don't know v final, but we have everything else. So I think what I want to do is I want to use this equation right here to find the final velocity. So the velocity actually at where it hits that 30 meter mark and the acceleration is about to turn off. So let's do that. We have v1 squared is what we're solving for, and we're going to be solving for this, and that's equal to v initial squared, okay, which is 0, plus, and luckily that's plus, and our acceleration is going to be upwards, and we have y1 minus y initial. So we're going to be using this. Alright, well, I'm going to square root both sides, so v1 is going to now be equal to the square root of all this. Vi squared plus 2a y1 minus y I. Alright, let's put in our numbers. Vi squared is going to be 0, so this is just going to be 0. And now we're going to have 0 meters per second, and that's going to be squared, but that's still 0, plus 2, and now we have 13 meters per second squared, times 30 meters minus 0 meters. Okay, so v1 is going to be equal to 2 times 13, which is going to be 26 times 30. Okay, let me see, 26 times 30. 2 times 13 times 30 equals 780. And now we're going to take the square root of that. Okay, so the second function, square root that. And that's going to, that velocity is going to be at 27.93 meters per second. So this is going to be 27.93 meters per second. So now we know it was traveling at 27.93 meters per second at this point. Okay. So that's the speeding up portion. Okay. Now it's going to be slowing down as it's moving upwards to its maximum height. Okay, and it's going to get to some maximum height at negative 9.8 meters per second. Now that I have that too, I think what I want to do is I want to find the time it took to get to that height too, just to be safe. I want to have as much information as I can. So I'm going to actually use this to solve for T final, and that should be T1 minus T initial. I want to just do this real quick before we do the slowdown portion. So now I'm going to solve for this T1, okay? So I'm going to subtract VI onto the other side, so V1 minus VI. And the reason why I'm doing this is I don't like not having all the information. It makes me feel uncomfortable, right? So this equation I'm going to eventually be solving for T1, so I want to find out at what time that 30 meter mark occurs where our velocity was at 27.93 meters per second. So now I'm going to divide both sides by that acceleration, V1 minus VI divided by A, and then I'm going to add to both sides our initial velocity, our initial time, which is 0, which I don't need to do. So now the V1 is 27.93 meters per second minus 0 meters per second divided by 13 meters per second squared. And so that T1, so the time that all this occurs, it's not going to be 4 seconds. Is going to be 27.93 divided by 13. Okay, let's try this again. 27.93 divided by 13 equals 2.14 seconds. So the engine shut off at 2.14 seconds. Okay. So now that we know that, well, now let's do the top part of the graph where we have the slowdown portion, where now we know, let's fill in some of the blanks here. And I only put these numbers in for reference, that this actually occurs at 2.14 seconds, and that its velocity at that point is 27.93 meters per second. And so it's sped up from 0 at that acceleration so it was accelerating upwards, and when it hit the 30 meter mark it was traveling at 27.93 meters per second upwards, and at 2.14 seconds the engine shut off, and now it begins falling down. It's basically slowing down from 27.93 to a velocity of 0 at some other point in time up here. Okay, and gravity will be pulling it down and subtracting off from this velocity 9.8 meters per second for every second that it's now moving upwards until it comes to a stop. Okay? Okay, well, now it is in the slowdown portion, and we're going to rewrite some of our variables. So in this slowdown portion, it's traveling at 27.93 meters per second, and this is at T1, which is 2.14 seconds, and its y direction position at that point is 30 meters. Well, now it's going to be accelerating downwards at g, which is going to be negative 9.8 meters per second squared, and the negative is because that acceleration vector is downwards. Now what we're going to try to solve for is the height that it gets to, which is going to be y final. That is ultimately what we're going to be solving for. And at that y final, the final velocity is going to be 0 meters per second, because it's going to be coming to a stop. Otherwise, it would keep moving upwards if it had any more speed to it, right? So we want to find this, and this is what we're given. Okay, we don't have that at that point in time that it occurs. Okay. So we're going to use our equations of motion. We're going to be looking for any equation that doesn't have t final in it. Okay. Okay, so we're going to be using that equation that we used before. That's kind of funny. So we're going to be using this same equation right here because it doesn't have a time variable. It has final velocity, which is 0. It has the initial velocity, which is 27.93 meters per second. It's going to have a negative gravity and y final minus y1. Okay, so I'm going to write that here, and I'm going to be applying our vectors to it. So we're going to be we're going to be using v final squared. We have v1 squared, which is 27.93, minus, because this acceleration is now g, and that's going to be equal to y final, which is the maximum height, which is what we're solving for, minus the height when it was at 27.93 at 2.14 seconds, which is going to be 30 meters, which is going to be y1. Okay, so we need to solve for y final right here. So we're going to be doing the same kind of algebra that we were just doing before. Just for one note though, it is not moving here at the end. So that is 0, which is going to make our math a little bit easier. So we're going to subtract v1 onto the other side. So v1 squared, and that's going to be equal to negative 2g y final minus y1. Okay, multiply both sides by a negative 1, which is going to be v1 squared equals 2g y final minus y initial. I just multiplied both sides by a negative 1 and just made that negative both positives. And now I'm going to divide both sides by 2g. And then we get this, y final minus y1. And then I'm going to add y1 to both sides. So v1 squared over 2g plus y1 is equal to y final. Alright, well now let's put in our values. v1 squared is 27.93 meters per second, and I'm going to square that. I'm going to divide it by g, which by taking that negative out, this is now just the magnitude of g, which is just 9.8, so it's going to be 2 times 9.8 meters per second squared. And then we're going to add to that the initial, that position when it was at 27.93, which is at 30 meters, which is equal to y final. Okay. All right, time for the calculator. 27.93 times 27.93 meters per second is 780. I'm going to divide that by 2, and then I'm going to divide it by 9.8. So this part over here is going to be 39.8 meters. Okay. And then I'm going to add to that 30 meters. and that's Y final. Well, that works out to be 69.8 meters is Y final. So now we know that this rocket, which sped up to from 0, it sped up to 27.93 meters per second in 30 meters and over a period of time of 2.14 seconds, then slowed down to 0. It then slowed down to 0 from 27.93 to its maximum height of 69.8 meters for the rest of that flight. And I don't know time, and the problem's not asking for it, so I don't need to solve for it. Okay, so this is how you do those application problems. So go ahead and try the last one, and we'll talk about it in WebEx. Okay, I hope you had a good time. Thank you.